All right, in this video I'm going to very quickly go through the how they model the normal shock and then some of the equations that are used to describe these shocks. Basically, it's going to really depend on the back pressure, so we're going to need to talk about these various pressures across this shock wave. Now, a shock wave is really small, okay? So it's going to be a little tiny differential balance on a very small section, somewhere in the diverging section of this supersonic converging diverging nozzle. All right? Now, because it's very small, it's going to have essentially no heat loss, so I can assume it's adiabatic. If I write my mass and energy and momentum balances, I end up with these expressions that are from your book. Okay, I also can talk about the entropy because we know that entropy is going to definitely be generated because this is irreversible. Okay, so now then I have a complete set of equations. I can use these and plot the curves, okay, of these various things. Now there are several that are used in particular. Okay, so first one is called the Fano line, and the Fano line looks at the mass balance and the energy balance equation and the H values of H and S that make that true. If I look at, well, okay, I'm having a hard time getting my slides to move. Okay, if I look at the mass and momentum equations together, then that's going to be what's called a Rayleigh equation. Now, this is solving two of those equations simultaneously. This is solving a different pair simultaneously. So where these intersect are going to be the 2 points, the inlet and the outlet, that are going to describe where this normal shock is going to happen. Okay, so the intersection of the Fano line and the Rayleigh line is going to describe for me the location of the shock. Okay, so it's my upstream and downstream states on either side of the shock, what I'm going to find there. And if I take this and come up, okay, just looking straight up and down, a distance velocity squared over 2. In other words, take from this and go to H naught, that stagnant state. Okay, so remember H naught was H minus Vx squared over 2, or plus, excuse me. Okay, if I do that, I'm going to find that it's going to be the same value of H naught for both X and Y, the downstream and upstream states for the shock wave. Okay, one side's going to be subsonic, one side will be supersonic. Okay, now we say that we're modeling this stuff using isentropic flow. And so now then we can take and kind of combine these things, and people have done this for us, but they look at the stagnation state and the actual compressible flow state, and people have tabulated these as ratios. There are equations, so if I want to use data, it's in tables. If I want to assume constant specific heats, then I need equations. And people have done this. And so if I had something where I thought specific heat was not changing much, I could use these equations to find the temperature of the stagnation state, the pressure at the stagnation state, and the ratio of the areas where the area is going to change over, that critical area. And all of these equations are tabulated. We also can do this for this in tables, since it's the same stuff. Now these are all for constant specific heats, but there are tables in your book where these things have all been done, so you can estimate the stagnation state very quickly based on the value of the Mach number. At this stage, we're ready to now go ahead Oh, wait a minute, there was one more equation. Ratio of temperatures across the shock and ratio of pressure across the shock. What we're going to do next is we're going to shift gears and we're going to look at automotive engines. I'm going to do a video that's going to quickly introduce that, some basic terminology. I'm going to then give you some references to some videos that I like available on the web that other people have created that are good, and we'll really show you how some of these models relate to an actual car engine. And then in class this week, we will actually be looking at these cycles that describe automotive processes.